An LED head torch from China. This one is quite interesting for a number of reasons. Firstly, it's quite heavy. It weighs in at about 143 grams, 5 ounces. It has two modes. You've got the little switch in the bottom that slides backwards and forwards. It will select either a 6 LED cob array, which puts out a splash of light, just a general sort of wash of light. And you've got the focus beam, which looks like it's got a 1 watt LED in it, which puts out a fairly tight beam of light. There are two ways to charge this. It's got the little solar panel on top, and if we calculate from the size, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, that's about half a volt per section. It's about 5.5 volts, but it's really small sections. I would be surprised if this put out more than 20 or 30 milliamps. The other way to charge this is to just flick the little lever on the side and pop the two pins out, and then you can plug it straight into a 110 volt to 240 volt socket, and it just sits and kind of trickle charges the battery inside, I'm guessing. I did put it in charge. After a while it made bubbling noises. That gives a clue as to the technology inside. Because of the weight, this thing, it's got the strap that goes over the top of the head as well as the one that goes around the head, and I have to say it's a close fit on my big head. It does fit. It needs the extra tightness really to hold the weight of this. Also, it's got a little pivot here with a nut at one side and a screw at the other. I had to tighten that up because when I first got it, anytime you leant forward, it just flopped down and smacked off the nose. It's very, very heavy. So let's take it to bits. Oh no, let's plug it in first and put it in charge. Things it says: solar panel, allow 24 hours for full charge. AC 110 to 220 volt, 50 Hz, allow 11 hours for full charge. A full battery charge lasts for 10 hours of use. Those figures don't add up, not unless they're working on the basis that as the voltage of the battery goes down, the intensity will get dimmer and dimmer, but it will still be lit, which kind of works. Caution: fully charge the battery every 2 months when not using the appliance for an extended period of time. Failure to do so may shorten the battery's life. That would also hint at the sealed lead acid battery, because they do not like being left in a semi-discharged state. Do not charge the battery for over 24 hours. That would hint at trickle charging. Do not use the appliance while it is charging. I suppose really the only way to do that would be to have a mains lead just basically stuck on the side of your head. Keep the appliance dry. Do not leave the appliance underwater in a humid place or in a place with high temperature. Okay. And it's available in two colour schemes, black with a red front, or this one blue with a black front. Okay. Box out the way. Let's test it for power. So this time I'm going to use, the Hoppy will not measure this. This will measure it. The Hoppy does not like extremely poor power factor loads. This has almost certainly got a capacitive dropper in it. If I plug this in, it's already displaying. It was displaying, not sure why it glitched there, was showing like a wattage, but it's displaying nothing now. Let's plug this in. The little red LED is lit and is flickering. It displays 0.4 watts. 250 volts is the current supply voltage. That's nice. It's drawing 61 milliamps. The power factor, it's doing its best. It's displaying a 0 power factor. We'll try and work out the power factor later on based on the circuitry. It's going to be terrible. Well, it is terrible. It's pretty much 0 power factor. Peak was 2.5 and low. It's just yeah, we can ignore those. It's very low power, so it's kind of messing up its ability to read. These things are kind of designed for up to 3 kilowatts. So when you plug something that's only about half a watt in, it's at the lower range of its accuracy. Let's get that out of the way. Let's open this up and see what's inside. Screwdriver. That's a bad start. Let's try this one. No, that's not going to fit down. Oh, right. Should have thought this. Should have tried this beforehand, shouldn't I? Let's try this one. It might be a bit small. No, it's working. That's fine. Have I already? I probably have. This was probably insulated much further down. I've already cut a bit off because these insulated drivers, they're not ideal in all circumstances. Sometimes the insulation goes down too far. So let's get the back off this and see what's inside, then reverse engineer the charging circuitry. That's assuming I can get the back off. This screw doesn't feel like it's turning. This might be the wrong size of screwdriver. Oh, it is actually, because I can see it coming off. Let's retract the pins in. It is a sealed lead acid battery. That's interesting. It's got a little plastic fin there that not only holds the cob in. I don't know if you can see that. Let's bring it up, put some light in there. Can you see that little plastic thing that pushes the cob against the front, but also holds this LED onto the back of the reflector? Let's pop that off then. The solar panel has a connection from that side and the other side, so that's not going to come out easily. Is this going to come out? No, it's not. Let's try unscrewing this. So the light and the front reflector assembly is, it says, high bow. It's got the standard 1 watt LED. Oh, you know what? It looks like a star on that plate. Let's pop that off as well then. I don't need this one. I could go back now. I've got better reach. I could use the other screwdriver, but I shall keep using this one because I've started. So I'll finish. It's using a very standard Luxian star, so it's serviceable in that aspect. That also lets me get this out the back. It is just a standard Luxian star style LED. When the 1 watt LEDs first came out, a company called Luxian created a form called the Luxian star, which is this aluminium heatsink plate in a star shape with the thin shim of fiberglass PCB in the front and LED in the front, and it's just become a standard. Let's see if the cob array is stuck on with sticky tape initially before that clamp gets put in. It's the little aluminium plate with the LEDs in the front and the sort of little barrier and the fluorescent gel, the phosphor gel. And it's got a couple of holes and it's just placed over this reflector. Simple enough. Is that not those wires? No, they've got a recess out so that the chromium coating doesn't short those out. It's fairly close though. The battery itself, let's see if we can get this stuff out. Ooh. There is a resistor feeding out to both the switches. The resistor has a value of, orange, black, gold by the look of it. That's quite odd. 3, 0, and then gold is the divider. So that should only be about 3 ohms. Let's measure that. That would kind of make sense. Let's put this to the 200 ohm range. And I shall see what this meter is going to read. Just shorten the reads together. It's about, say, about half an ohm-ish. So this should maybe read about, if I can get this on, about roughly about 3.5 ohms. Yeah, it is a 3 ohm resistor. So that's the one that's limiting the current to both LEDs. It's quite a low value of resistor. It's just a 1/4 watt resistor. That's quite odd. And literally the LEDs just have one red coming from each of these and then a common green for all the... Well, the common green is not, it's not a common green for the negative. Common green is also being used for the mains ingoing supply, which has some sliding contacts there, so that when you slide this out, it just basically rubs against these connections. Let's get the circuit board out. It's not complicated. It is not complicated at all. The one thing that's confusing me here is that it does have 6 diodes. That's odd. I would have expected maybe 4 diodes. I'm guessing maybe the LED is just being driven by something there. What's the capacitor value? It's 1 microfarad, the capacitor. That's quite a high value. It does have a discharge resistor across it. I'd probably have screamed at a little pig if it didn't. Green, blue, yellow, 560k. Right, tell you what, I'm going to doodle this down. I'll be back in a moment. It is reverse engineered. If you want to try reverse engineer yourself, here are 2 pictures. One is the front of the circuit board, one is the back, but this one has been flipped and swapped around so that the bottom left-hand side of this image is the bottom left-hand side of this image. So these, you'll see from the tracks that they all correlate. The only component that's not really visible in this circuit board is the 560k resistor underneath that capacitor. This one here. So I'll just pause momentarily if you want to take a snapshot of that, and then we shall continue. The 4 diodes here are forming a standard bridge rectifier. The other 2 are purely for the solar panel to be able to charge the battery and also to light the LED to show it is charging. The schematic, I should put that out the way. The schematic is like this. The AC supply came in and they say 110 to 220 volt. It's a 400 volt capacitor, so technically speaking, it can go from, and it's dropping it down to 4 volts. The lower the voltage that you charge it with, the AC voltage, the longer it's going to take to charge. It's just going to be a difference in current. But you could technically use this way down to 50 volts AC or even 12 volts AC. It would take a very long time to charge it that, but it will go down to a very low voltage. But the AC supply comes in and you've got the standard capacitive dropper. The capacitive dropper has 2 metal plates, an insulator in between. That's what's in here, just on a sort of large scale. And on each half cycle, it allows a charge to alternate on that plate, so it lets a portion of current through in each half cycle. There's a 560k resistor across that. That's to stop you getting a zap off those pins if you left them out, if you unplugged it. If it wasn't for this resistor, bring that voltage down quite quickly, you could get a sting off the pins. That then goes through this bridge rectifier. It's a full bridge rectifier of 4 diodes. And the output then goes straight to the sealed lead acid battery, which it is. It's a little lead acid battery. We shall explore that afterwards. I took one apart some time ago. I dug out the bits. There's lead in it, which is no great surprise. So that charges the battery, and from the negative is common to all the things like, I've not even drawn the LEDs on. It doesn't really matter. Let's draw them on right now. So we've got the LED for the 2 different LEDs, one for the main beam, say that's the 1 watt one, and we'll call that the cob. The cob is actually 6 LEDs in parallel. And there's a switch that comes from that battery, and I'll just jump over that track there. There's a resistor, the 3 ohm resistor, and then a switch that can go between those 2 LEDs. So it's got a mid position, and then it can go to actually make the LED light up. Okay, continuing on, the other option for charging is the solar panel. Now, when it generates current, and I've measured that, pressed right up against one of my 20 watt lights here, it was putting out 30 milliamps. So on a good day in really bright sunlight, it could put out somewhere in the region of 50 milliamps maybe. It's not very highly rated, but it's reasonable enough. It'll do the job. It's certainly put out decent current. When it's putting current out, it will then charge the battery just via this diode here. And it will also make this LED light, the charging indicator, by passing current through that diode, through the LED, and through this 330 ohm resistor. That LED can also be lit from the AC side when it's charging. By this track here will then supply current to that LED. And that will be capped at this point. The voltage across here will be effectively the 4 volts across the sealed lead acid battery, plus a couple of diode drops. So say maximum of 6 volts on this connector here. The diodes are all 1N4007. That's a typical, very common, it's a very standard 1 amp diode. The last digit indicates the peak inverse voltage. In this case, it's 1000 volts. It's just used everywhere for mains voltage rectifiers. You'll often see other versions of that, like 1N4001 is rated about 50 volts. There are advantages to using the lower voltage, peak inverse voltage one, in the sense that also the forward voltage is slightly lower as well. But that's all a moot point these days in the days of Schottky diodes. I'm just digressing here. That's fundamentally it. Let's take a look at the lead acid batteries. So here is the little lead acid battery inside. It weighs 50 grams, 1.8 ounces, and most of the weight will be lead. What did you think they were going to do with all the lead that they couldn't use in solder? Because there was a whole industry around making stuff out of lead. So now they're putting lead batteries into products. And I wonder why they chose this over maybe a lithium cell. Because lithium cells are very, the amount of materials in a lithium cell is much lower for the same energy density. I'm guessing it's just the desperation of the fact that in the same way that when the European government banned tungsten lamps and all the Chinese lamp factories then switched to using all their glassworking skills to make LED filament lamps instead. It's all the same machinery and the skills of the people. So ultimately, I guess, instead of just shutting down a huge section of Chinese industry, they diverted to making little sealed lead acid batteries that can be used in products like this. I'm not sure. It doesn't sound nice having a lead acid battery strapped to your forehead, but I suppose maybe it's safer than having a lithium battery strapped to your forehead. It's never going to end well if something goes wrong. So the construction inside this, it will have two little wells inside it. There'll be a divider in the middle, and there'll be lead plates. And this lead plate will be looped over to this lead plate because each lead cell generates about 2 volts. And they'll come out and up to the top. I suppose they're probably quite easy to solder onto because they're lead. I don't know what the interface is to that. Where is the units I took out? That's the one that loops over. You'll notice these are 2 different colours. You've got the traditional grey lead, but this one's a much darker colour. I guess this is the sulfated one because the process of operation involves sulfation. I don't see how this is connected. Ultimately, I guess it must just be the lead must come up onto maybe an interface, or maybe that is the lead sticking at the top and they've just melted solder onto it, which is lead-based solder, possibly. Well, it is now. So the principle of a lead battery is normally, if you have a car battery, most car batteries are still lead-based, you'll have, each one will be filled with an electrolyte, but you can't really do that here because if it got tipped up, you could get liquid dribbling out. The car batteries are really just designed to be mounted up one way. So they have what are called sealed lead acid batteries where the electrolyte is trapped. And the way they trap it, they use fiberglass material, just basically fiberglass fiber. And it soaks up the sulfuric acid. It's a mixture of water and sulfuric acid. So they've basically put that wadding between those plates and that couples them together. And when you charge it, it's quite interesting. It's, as far as I can see, it's just standard lead. There are quite complex chemistries for higher current applications. They're not using that here. This looks just like plain old lead. Let's find out. Let's scratch it. Let's scratch one of the lead plates and cut it. So it feels like lead. Oh no, actually, you know what? This might possibly be a little lead dish with, it's got the lead oxide type paste pressed into it. Okay, and a texture on the front that's probably incredibly toxic, maybe. I doubt it really. But I'll try avoiding eating it. But what happens when you're charging it is the sulfuric acid sulfates the lead, and you end up with a sort of lead sulfate compound. And I'm guessing that's possibly what's happening here in the change of colour. And in the process, as you charge it up, the amount of acid in the water gets less and less until theoretically, if it was in a fully charged state, beyond fully charged, the resistance of the battery would go way up because all the acid would gradually leave the water and you'd end up with just plain distilled water. So there is a delicate balance. Also, when you charge them, if you charge them too fully, as happened here when I was charging this, I could hear sort of crackling, bubbling noise, and it was tiny little bubbles of gas coming off this, and the pressure would increase inside, and there are vents to basically let that vent out. I do see the little caps here, little rubber caps, and they've sucked down. They have sucked down. Let's pull the cap off. This would theoretically also, taking this cap off, it would let you top these up, but I'm guessing this little cap here It's a soft, squishy rubber cap. That over the top means that if that's just held in place loosely from the top, and that is now, it's not sucking down like that one, the pressure build-up will just ooze. It will blow that sort of rubber cap. Hold on, let's draw it. So we've got our little port here with the hole up the middle, and we've got this soft rubber cap over the top. I'm guessing it'll just basically, the pressure will just ooze out the side of that cap. But in the case of this one, when it's been discharged again, that pressure has gone down, or that maybe it's thermocycling, and it's domed that in, it's actually sealed it. So that must be effectively not just a filling cap, but also it's acting as the pressure relief. And it's simple enough, you can pull this little cover off. Theoretically, that means that if one of these cells get really nuked and dried out by overcharging, because it gradually loses, it splits the water into oxygen and hydrogen, it vents out as gas. That's one of the biggest dangers of battery charging banks, where you get a build-up of gas. And sometimes if there's a spark as someone disconnects a battery while it's charging, and this is why you shouldn't really disconnect batteries while they're charging, especially if the top's open, it can cause an explosion, a hydrogen-oxygen explosion. And if that flashes into the battery, the whole battery, in the case of the car batteries, can explode and spray acid everywhere, which is an absolute delight. So now we've found where all the lead's gone since the reduction of hazardous substances. It's gone into these batteries, which are being disposed of in landfill as well. And we know that the fiberglass mat in here is soaked in this sulfuric acid and water. As the battery charge, it sulfates the plate, and one of the biggest problems with over-discharging batteries is you end up with a build-up of a hard, crystally sulfate that actually makes batteries go high resistance. That's what happens when you leave car batteries over-discharged, because lead-acid batteries, they like to operate between the range of, I think it's about 1.8 volts per cell, up to about the maximum charge voltage. We can work that out. Car battery has 6 of these cells in it. So say maximum charge voltage 14 volts divided by 6 equals, it's looking for a maximum voltage about 2.3 volts before it's regulated. When you're trickle charging these, it will go up to the sort of upper voltage level, and then it will just keep outgassing. This is why you can't leave it charging. And many alarm systems, burglar alarm systems, use a sealed lead acid battery, and just gradually over time, because they're continually just kept topped up with trickle charging, they lose their electrolyte and they dry out, and you end up that when there's a power cut, the alarm goes off because the battery was flat. It's always worth checking the batteries in your alarm systems. But that is it. It's interesting. Interesting construction of these batteries. Interesting use of a battery that weighs a ton inside a really bulky head torch with just basically everything thrown at it. So I'll be keeping a few of these components. I will not be putting the thing back together because it's all a bit pointless, but I do like the little clamp here for holding a Luxian star into the reflector. I'll keep the little circuit board, possibly use it for scavenging components. Other than that, and I'll keep the cob array. Let's pull that off, in fact, since I don't really plan putting this back together. I usually do put stuff back together, but sometimes it's a bit crap and you think, ugh, no point. It's just going to end up sitting around for ages. Let's see if we can get this off. It is actually jammed onto those pins. Is it glued? It does almost feel like it's glued. I think it's just a very tight fit. There's the little cob. I shall keep that. That will operate at about 3 volts. But there we go. I'm not sure I'd recommend this. It's an interesting little light. It works. It's very big and bulky and heavy. There's much lighter, smaller ones that will fit in tool bags easier and are more comfortable to put in your head. But very interesting to take apart anyway. It's definitely one of those sort of scattergun approaches using generic circuit diagrams that they've done. It's got strong semblances to for instance, the Death Dalek lights, the ones that basically used nickel metal hydride cells or nickel cadmium cells, and then just hooked a USB port over it so that it was connected to the mains. Those are completely different videos. If you search my videos for Dalek, you'll find those horrible camping lights that put 240 volt or 120 volts out to your phone's case if you plug it in while they're charging. Lovely. But there we go. Interesting, well worth taking apart, quite enjoyable taking apart.